Thank you so much for being here. We're really thrilled to have you all. I'm Amy Stout. I'm the head of quantum product strategy here at SAS. I'm joined by my colleague Josh Griffin. He leads our engineering efforts on the quantum side. We're super excited to spend the next 25 or so minutes with you talking through the SAS Quantum Lab. This is our new and first quantum capability that will be surfaced in SAS Viya later this year. It's currently under development, and we look forward to sharing this with you all. Before we jump into the SAS Quantum Lab, let's start with a brief Quantum 101. Let's ground quantum in the real world. So if you think about why organizations across industries are starting to take notice of quantum, a lot of organizations are already actively investing in quantum and working in quantum today. The reason is there is a high potential for quantum to solve very high value business problems that will have material economic impact. So what exactly does that mean? Well, let's take supply chain, for example. As the number of interactions grow exponentially in your supply chain problems, currently classical computers will give us an answer, but everyone understands it's really just an approximation. Quantum's promise is that we will get better decisions, more accurate decisions, because it can more effectively search that complex solution space. What that means is it could translate to hundreds of thousands to millions of dollars of savings in your supply chain. Now, let's look at another industry in finance. Things like portfolio optimization. Similarly, with very complex problems, let's think about portfolio optimization. When the number of variables grows in that exponential realm, again, there's a lot of different scenarios that you can be looking at, a lot of different possibilities. Today's computers, we're doing it. We have portfolio optimization across banking. However, again, it's an approximation. The classical computers cannot keep up with that level of complexity. So quantum computers, once they are sufficiently mature, are expected to help with that type of complex problem. So quantum can help in the future with these complex problems, but it can also help with problems that aren't really solvable today. So in pharmaceuticals, think of things like new drug discovery, protein folding, molecular modeling. These are things that classical computers, the most powerful supercomputer today, cannot do. It is intractable, not feasible. That is what the promise of quantum computers bring. Now, let's take a look at what quantum actually is. So quantum is an entirely different method of computation. It has new hardware that's based in quantum mechanical principles, and it also leverages new algorithms and software in order to help with those problems. Now, it's not going to replace classical computers. It will be used alongside our existing CPUs and GPUs. We will now leverage QPUs, or quantum processing units, to help with those hardest decision points across our problems. So you're still going to see this familiar data and AI lifecycle. Now you're just going to be plugging in quantum to help get better decisions. Now, you've probably noticed on this page and the previous that there's some asterisks, and we're talking about the future and what quantum can bring, what it will bring. The reason that is because quantum today is in its relatively early stages of development on the hardware side as well as the algorithm side. So there's this heavy push toward quantum exploration. You see a lot of leading organizations across industries that are building teams. They're starting to build out intellectual property and algorithms for how to use these quantum computers. Once we reach what's called quantum advantage, you might hear the term fault-tolerant quantum computing. That is what everyone is marching toward, where we can actually get those measurably better decisions on mature hardware. But today, there's still a lot of discovery and validation happening on these more emerging types of hardware that's available. So SAS last year in 2025, and again this year in 2026, conducted a survey on over 500 global participants across industries. And these business leaders, over 60% of them said that they are actively investing in or exploring quantum computing today. But there's a lot of key barriers to entry that are holding them back from really driving quantum exploration home. Some of the key barriers include uncertainty around practical real-world use cases, high cost of implementation, and lack of trained personnel. That actually reflects exactly what our quantum team at SAS has been seeing in the market as well, and it's something that we have experienced in our own quantum exploration over the past few years. We realized that if we want to help get not just ourselves, but all of our customers ready for this ROI of quantum in the coming decade, that we needed to find a way to level the playing field. And that's exactly why we are creating the SAS Quantum Lab. Like I said, this is coming to VIA customers later this year in Q4, and it is a practical launchpad for organizations to get started and to scale their quantum AI journeys. Across the market, we do hear about those three main barriers: the uncertain business value, the high cost, and there's a very steep learning curve. So we designed this product, Quantum Lab, specifically and intentionally to address all three. So first, let's talk about lowering the skills barrier. Quantum Lab has been built in a way that we're trying to help teams learn as they go. So rather than needing deep quantum expertise up front, we're providing a virtual quantum AI tutor that will answer your questions. It will provide sample code, and it will suggest next steps for you so that as a user, you can build understanding while you're experimenting with quantum. Second is proving that value. So Quantum Lab makes quantum experimentation really tangible from day one. Customers are able to compare classical, quantum, and hybrid approaches side by side for their real-world industry use cases. This allows teams to clearly see where quantum can add value, and just as importantly, where it doesn't. Now, this is something especially that we're really excited about with SAS, because as you know, in your VIA environment, you're using this in your everyday real-world scenarios to make better decisions in your business. So we are allowing quantum experimentation, quantum exploration to be a part of that journey rather than an entirely separate investment or thought process. It's baked into your entire data and AI workflow. And finally, reducing cost. Quantum experimentation today gets very expensive, and it can also be very inefficient. So in our current tests, our Quantum Lab has delivered runtimes of up to 100 times faster with Quantum Lab versus doing the same type of quantum experimentation outside of SAS Quantum Lab, in addition to an up to 99% reduction in compute costs with that same comparison. Josh, in a little bit, will go through this in more detail. We'll get to see it live with a demo. And this, of course, is dramatically lowering one of the key barriers to entry of how expensive and time-consuming exploring quantum can be. So that sounds really exciting and kind of crazy if you think about it. So how does this actually work? Let's look at a real-world example. So for those of you who have gotten started on quantum, you've done a couple of quantum experiments before, you are probably already aware of the massive number of iterations that it takes when you're experimenting with quantum. Based on the number of circuit variations that you're testing, if you're not familiar with a circuit, it's essentially the instructions for the quantum computer. So in that exploratory era that we're in today on this near-term quantum hardware, a lot of people are building different circuits, running their data against that. You're doing a lot of different jobs that you're sending to the machines, be it simulators, which are it's a classical version of simulating how a quantum computer might work. But then you're also going to be running on the real quantum hardware, even though it is not sufficiently mature yet. You're still going to want to see how it actually works with things like superposition, entanglement, and the types of noise models that a real quantum computer would have. Now, you will also be doing that many, many times. So an industry standard for this type of problem, this is a quantum reservoir computing example for fraud detection in the finance space. You end up doing maybe 1,000 shots. All of this combined for, again, just a pretty small data set with 1,000 samples gets you to 100 million quantum iterations. Now, when you're doing that on the simulators, that can become very time consuming. When you're doing it on real quantum hardware, those costs can start to grow pretty quickly. So that's something that our team, when we were getting started with quantum, recognized as how can we make this better for ourselves and then ergo for our customers. In a moment, I'll walk through the three capabilities that really enable that, but just to put this in perspective of what impact this has, let's say that an organization is given $250,000 for the year in that finance example to explore quantum, various quantum problems, whether it's fraud detection, portfolio optimization. with that $250,000 budget, in today's world, you really can't even get through one problem if you're going through that entire experimentation that we just walked through. With the Quantum Lab, not only can you do that problem in full, but you can also do over 150 additional experiments and problems. So how does this work exactly? We have capabilities in the Quantum Lab called AutoQX. AutoQX is comprised of three core things. First is parallelism. So parallelism solves that issue of slow simulators. This runs our jobs massively in parallel so that we can far more efficiently be getting these results over and over rather than waiting for the sequential runs that you typically need to do in a quantum problem. Next is caching. Caching is what enables you to avoid redundant and expensive quantum jobs. Right now, when you're manually doing quantum experiments on your own, typically you're going to be just sending the job over and over again. And at some times in that experiment, you already have a certain portion of the answer locked in, so you don't need to run it again. That's what caching does. It saves that answer so that you're only sending what you need to be ran to the actual hardware. And then finally is auto-tuning. So this is where we gain a lot of efficiency. This helps you find the most optimized quantum circuit parameters, both classical and quantum parameters, at basically the speed of light. That's probably hyperbolic, but it does enable you to look through this entire solution space of your quantum experiment far more quickly and efficiently than the current method, which is manually changing your number of parameters one by one and seeing what the impact is. So to bring all of that together, SAS Viya really accelerates your quantum journey with the SAS Quantum Lab. Our goal is to help customers make real progress with quantum AI starting today, enabling you to move from curiosity to capability. Now I'm going to hand it over to Josh to walk us through a demo of Quantum Lab.
So can everybody hear me? Great. Okay. So unlike Amy and Bill Wysocki, who hopefully you saw some of his great presentations yesterday, my team, when tasked with creating a quantum product a year and a half ago or so, were brand new to quantum. And I think this was a unique advantage for us, ironically, and that I asked my team to keep track of every pain point, every friction point, every bottleneck, everything that was annoying, everything that made us feel like we were going through molasses. And then let's remove all that. Let's create a quantum freeway where all of this is really easy, fast, and intuitive to do. So the same pain points that you picked up on and highlighted, we felt them as well. And with this Quantum Lab, it's the thing that I wish I had when my team started from scratch to fast track and move light speed ahead at quantum. So let me pause this. Oh, let me go back one, sorry. Can you help? Sorry,
The clicker only goes
one way
yeah, but you can just use this.
to pause it. Okay, all right. Cool. Okay, this is meant to be a 50,000 foot view. Please come to the lab if you want us to slow it down. Definitely don't try to read all of the text that the tutor is saying. I'm going to summarize that for you. At most, read the questions that the theoretical consumer is typing and look at the outputs, and I'll walk you through it. And this is trying to show you all the ingredients and also fast forward track from a phase where you just want to get all of your questions and concerns answered, learning in a language that you would understand in SAS, and then phase shift into doing something actually practical and doing real life quantum analytics with very little need to know about what the circuits are you are using. No, we don't expect you to write your own circuits. We're going to give you the ability to do so. But we're also going to give you a circuit zoo so you can fast track that. And then we're going to, as things become more complex, we're going to add more tools to simplify that process. So each step of the way, hopefully will be a delight for you. I did it again, sorry. How do I, what button to start it? Sorry, I'm very sorry for this. Okay, so when you ask about quantum in our, the Copilot is going to flag the agent that you're interested in quantum. We've created an agent, we're calling her Professor INTA for entanglement short. and she's going to figure out what level you are at. In this case, she's starting at ground zero, learning about superposition. She's going to create a hello world circuit or a quantum program that essentially is going to put one qubit in perfect superposition and measure it. At this point, you'll say, well, wait, this is just like flipping a coin. And you can ask this question, and she's going to tell you, yeah, but something more mysterious is happening in that coin is actually in a waveform when you're on a quantum computer. It's both 0 and 1 at the same time, and that's where that massive quantum parallelism starts to spark. And then to truly understand, you have to start to scale up. So they're going to ask to do more than just 1 qubit. Here she's going to show you how to do with 2 qubits, and you can keep going 3, 4, and see how things start to scale. Now that you have 2 qubits, what you see is now you have 4 bit strings. And again, this is heads, tails, tails, heads, flipping 3 or 2 fair coins. But you'll start to see that, did it pause? Oh no, it's still going, okay. Slower for some reason. Okay, and so this is where you can start to hint at the power of quantum computing, because if you were to add another qubit, you would have 8 bit strings coming out, not 6. And so you're growing at a factor of 2 to the n. In fact, by the time you get to 300 qubits, you're controlling a state vector who has more entries than the number of atoms in the known universe. So that's where you start to work with unphysically large numbers, which is kind of amazing. And they're hinting at that. And so now, how do we control that? Now that we're working in this massively large space, well, the next magical thing we'll use is something called entanglement. And what entanglement does is it allows you to bias the frequencies of these bit strings towards solutions. So you can make it so that when you pass an image through a circuit, certain bit strings are more likely to happen when it's a cat than when it's with a dog. And so the hope is kind of like shining a light through a prism, refracts things so you can detect what lights are actually entwined in that flashlight. Same thing kind of works as well. And so you can ask any questions you want to learn about entanglement, and then at some point you're going to flip gears and say, I want to actually do something real. I'm done learning. So they said they're working in machine learning, and so they're giving a regular machine learning pipeline. And she's starting with what you know. So there's no quantum yet. It's just doing SVM machine, something hopefully you're familiar with. And it's going to show you gingerly how to insert quantum at the right places so that you can add quantum to the classical and compare them side by side. So see what the best classical you can get with SAS, which we're great at, and then also work as hard as you can to do the best you can in quantum. And that's how you can prove true value. And we'll show you the circuits. And again, you don't have to, you can turn it off, but sometimes it's nice to see. What's most important is you're creating effortlessly new quantum features on that input data to hopefully increase the accuracy, showing some patterns that normally you wouldn't be able to see without the use of a quantum computer. Now at this point you might realize there's a lot of knobs for you to turn, both for which model to choose, which circuit to choose, number of qubits, what hyperparameters to choose. This can feel overwhelming, but this is a problem that we're familiar with in the machine learning world, and we already have tools, auto-tuning, and SAS has a number of patented auto-tuning tools to help with this. I skipped ahead. So this is a step that, so we're creating steps so that we can hide the code, and this allows you to do the same thing without any code. So we're creating a number of GUIs that will hide the code. So if you don't like code, you can load these steps, plug in your data, choose different hyperparameters, and then be able to run them. And again, measure the best in classical, the best in quantum, and really be able to see if this is true value or an aberration. And this is where you can start to realize that there's a number of options that you can play with. And at that point, we're introducing auto-tuning. We've created a brand new proc called Proc Hypertune that allows you to take any SAS code, drop it into a submit block, and within minutes being able to auto-tune macro variables in parallel using multiple SAS sessions, multiple CAS servers. So massively parallelizable. And it'll try a lot of different combinations for you using smart algorithms to try to find the best in the space that you're looking in. All you have to do is drop in your data. You can choose the ranges, the models you want to look at, the number of qubits you want to range on, the number of classical hyperparameters that you want to do. You can use a caching system so that when you're running in circles, if you submit a job from before, we'll detect that. And we're clocking in at 97% speed up using this parallelism and caching. And theoretically, if you did 5% of these evaluations on a QPU, you're getting 95% cost reduction just by vetting a lot of these results on the simulator itself. And this parallelism, because quantum computing is embarrassingly parallelizable to the nth degree, you'll be able to really scale out very quickly, adding just a few nodes. So if the CAS server is a really great option, if you're maximizing a single node, adding another node is actually going to reduce the time by a factor of 2. So you can get the time down. We've seen up to 500x in practice, and we expect it to be pretty much unbounded. So here they've changed it to 16, doubled it, and you see it's 103x faster. And now at some point when you're done learning about quantum and you feel ready to start, you could tell the quantum tutor a little bit about yourself. Say you work in finance, and it will tell you different projects that you could do in finance. You pick the one that you would want to do, and it'll walk you through that step by step on how to set that up, how to vet it, how to make sure it's true value add. You can show it where you're stuck, the results of what works, what doesn't, and it's meant to be not just a tutor to help you learn about quantum, but to be your partner in the journey all the way to where you're doing cutting edge research. And with this tool, we were able to, last year, submit 9 patents very easily. So this isn't just for learning about quantum, but for doing real life quantum today. And it can grow with the technology and adapt. And we're trying to work really hard so that this is free to you with VIA, because we want to hear your feedback on this, because we want this to be the tool that you love and the tool that you would use. So if you tell us what you like, don't like, our team will work really hard to adapt it to that information. And thank you. Wow, I really flubbed that one. Sorry.
Thank you so much, Josh. So like Josh said, and this is actually currently under development. So if you have certain things that you saw that you're really excited about, please come tell us. We will be at the booth today. Send us an email, find us on LinkedIn. We want to make this the most useful quantum tool, not just for ourselves, but for all of you. So if you're interested in a very live demo, we're doing some of those at the booth today, Wi-Fi pending, hopefully all of that will run smoothly. And we're looking to do some one-on-one sessions over the next couple of months with some people in the industry to, again, hear from you, either if you have looked at quantum before or even if you haven't. We want to see what would be most useful for you in your VIA environment for the Quantum Lab. So with that, I don't know, Cameron, if we have time for questions. Okay, any questions?
Yeah, who are you partnering with on the back end for the quantum compute? I said, who are you partnering?
Who are we partnering with?
Who are you partnering with on the back end for the quantum compute?
Yes.
Because last year you had D-Wave do a presentation. I'm not sure if you're partnering with D-Wave or a different company.
Excellent question. Yes, no, that's great.
Okay.
Okay, I want to make sure you can hear me again. So yes, excellent question. Yes, so the question was, who are we partnering with on the hardware backend? SAS, of course, we're not building our own hardware, so we have a number of amazing hardware vendor partners across industry. You asked about D-Wave last year, so yes, we are looking across, for those of you who aren't as familiar with quantum, there's multiple hardware architectures or modalities that are being developed across the quantum ecosystem. So D-Wave does what's called quantum annealing. We have another great partner, Quera, who does neutral atom. We had a great presentation with one of their representatives and Bill Wysotsky yesterday, if you were able to catch that. And we're also partnering with others like IBM Quantum for superconducting qubits, IonQ for trapped ion. And our team is constantly evaluating the entire landscape of quantum hardware because, again, our goal is to bring the best-in-class tooling for our customers. So in some cases, we might end up finding superconducting is great for one type of problem, whereas neutral atom is great for another type of problem. We want to be able to surface all of that to customers. Yeah. Particular. Good question. So the question, if you missed it, is are we targeting a particular sector, different industries? We are looking across industries. So as you may know, with quantum in general, a lot of the problems fall within either machine learning or optimization or simulation of nature, so things like chemistry. Those types of problems have applications across multiple industries. So we are targeting all industries. I would say that there is a probably earlier term focus, not for the quantum lab per se, although maybe if we're finding a lot of interest in those, perhaps we work on some targeted circuits to be determined based on y'all's interest. But I would say finance, pharmaceuticals, manufacturing, that's where we're seeing and hearing a lot of interest in quantum so far. But it will be cross-industry.
And we do have team members researching in those different diverse, like doing SQDs, quantum diagonalization for molecular study. And the reason it's AutoQX and not AutoQML is because that X means really anything that's quantum, we want to be ready to allow you, so as flexible as possible, while creating trails to make it easier for certain modalities over time to be done quickly. But at the lowest level, we have something like primitives so that you could really go in any direction you wanted at any level.
Does that help? Okay, we have one right here and then we'll come back to you. Cameron, do we have time for another?
Yeah, you can do.
Okay, a high-level question. What are things to kind of prime our brains? What are like things that quantum is good at and quantum is not so good at? So I'm trying to think like, is this for everything? Like my matrix multiplication is going to be faster, or is there things that it's not so great at that regular computers do great at?
At a high level, yes, there's you're not going to want to, it's in the same way that you won't use a GPU to write an email. You're not going to use a QPU for really still a large majority of what you're doing. If a problem can be done really well classically today, you won't need or want a QPU. Josh, I'd love your...
So a real easy rule of thumb to use right now is if you understand the concept of NP hard, QRAM hasn't yet been invented where you can put data onto a quantum computer and have it persist because the lifespan is so small. Therefore, quantum computers are going to be really good at problems where it's high on the compute side and low on the data side. So NP hard problems tend to be, and that's why they focus a lot on optimization. But if anything is NP hard, low on, the amount of data that describes the problem is relatively small, which like most operations research problems are on that side. But the amount of compute that exists is really high. That's the perfect for today's quantum computers. If ever they figured out how to solve the QRAM problem, that might flip-flop. But yeah, if it's a big data problem, it's probably not a quantum problem unless you can figure out a way to turn it into that high compute scenario.
Time. Okay, come find us at the booth. If you have any other questions, please come find us at the booth or reach out separately. Thank you so much for your time this morning. Have a great day, everyone.